So in this video, I want us to talk about the stack ADT, and we're going to discuss two different ways, two different data structures we can use to implement that stack ADT. So as a bit of a review, the stack is an ADT representing an ordered sequence of elements that can only be added from or removed from one end. And so one of the ways we think of visualizing a stack is using something like this picture at the bottom right over here, where you have a stack of numbers. And you maybe could think of them like a stack of lunch trays. And you always put the lunch tray on the top and take it from the top. You might remember this term, last in, first out, or LIFO. That's not the most commonly used phrase like day to day, but it's still good to hear that every once in a while. And the elements are going to be stored. We said they're ordered because they're going to be stored in the order of their insertion. So the first thing you put on, it goes at the bottom. And then if you put something else on top, it goes above that. If you put something else on, it goes on top of that. And so they're being stored in the order of its insertion. And when you remove from the top always. Now, importantly, even though they're ordered, kind of like a list is ordered, we don't think of stacks having indices. So we do not think of the stack as providing behavior to say, get me the thing at index 0 or index 14. And we only think of stacks allowing these behaviors I have in this pink box. The state is the collection of the ordered items, and maybe we'd also include the number of items. And the behaviors are pushing, putting something on the top of the stack, popping, taking something off the top of the stack. The rest is just looking at things in the stack, like peek to see the thing at the top, the size, which is the count of the items, and is empty is usually just a convenient one for is the count 0. But we do not provide like get of an index. That's a very, very important point because we want to simplify the structure so that clients can only add, remove, examine from the top of the stack. Now, here's an important point. An ADT, an abstract data type, is an abstract idea. There is no such thing as a programming language that has an ADT because ADTs are abstract, they're theory. We mentioned that Java, for the most part, uses interfaces to represent the idea of an ADT, describing what something should do, but not implementing how to do it. So a stack ADT does not exist in any particular programming language necessarily, but lots of programming languages include the idea of a stack that tries to implement this stack ADT so that people can use them because they're useful constructs. So one thing that can sometimes be confusing is that the specifics of certain programming languages can sometimes get mixed up with the abstract idea that we're thinking about in theory land about ADT. In particular, Java kind of really messed up the design of their stacks in the language Java. So they created the stack before interfaces existed. So there is no stack interface. There's a stack class, and that's it. Additionally, the Java people also decided, hey, wouldn't it be great if stacks let you get an element at any index? So the Java stack actually has a get method where you can say, get me the thing at spot 4. Now, it's okay for Java to do this. This doesn't break any laws because at its core, Java's stack still implements these behaviors. Push, pop, peek, size is empty. They still can be used in this in place of this abstract idea. However, they went above and beyond and provided a lot more functionality like get at an index. And so for the most part, I think it's good practice to avoid those extra behaviors, especially in the context of an algorithms course like this. Because one of the things we're going to be focusing on throughout this quarter is thinking about algorithms from an abstract perspective. Even though all your programming projects are in Java, we're going to be thinking about computation as something that can happen without necessarily a programming language. And if you get used to the idea of using Java stack by using its indices, then you're going to have a much harder time thinking about how to abstract away into more general purpose algorithms, where if we're thinking about the stack ADT, it does not provide that behavior. So this is kind of a long-winded way of saying that sometimes different programming languages make concrete choices about their implementations that slightly differ from our theoretical ADT. And so that's one of the things that's important to remember is that ADTs are abstract theoretical concepts. So let's think about some concrete ways of implementing the stack ADT. So one of the first things that I thought of when thinking about, okay, well, how could I go ahead and try to implement one of these stack ADTs in a concrete structure? Well, since everything is happening at the top of the stack, you only add and remove from the top of the stack, it might make sense to implement that using linked nodes, where you use a reference to the front to represent the top of the stack. And you can also keep track of a size. And then all of our operations are just in terms of this front. Instead of calling it front in this example, I called it top to make it a little bit more clear how this relates to our stack state. So say that you made a stack with these linked nodes and you wanted to push the number 3 on an empty stack. Well, top is going to represent the top of the stack. Since there's nothing there, we're just going to add a new node with the number 3 inside of it and increase the size to 1. Now, if we want to go ahead and push the number 4 should go on the top of the stack. And so all we're going to do is rearrange some of these pointers so that now that top points to 4, and then 4 points down to whatever was below it in the stack. And the reason it's nice to use this type of structure to implement this idea of a stack is that the field top is kind of where all the action's happening. So now if you want to go pop something off or move it, then all you have to do is just rearrange, just say, take top and make it point to the next thing after what top was originally pointing at. And that can then remove the top element. And so hopefully you can see that this is kind of a very natural way of trying to use data structure to represent a stack. Remember, this linked nodes would be a concrete data structure that tries to implement this idea of a stack. And so now that we have this idea down of how to do this, I guess I should also mention real quick, the other methods are fairly straightforward. Peak, you just look at the value at the front because it's right there at the front, that's the top. Size just returns the size field, and isEmpty just returns if the size is equal to 0. So now let's think about what the big O analysis of these methods are. What's the worst case runtime? Now, I'm going to warn us, we're going to still be a bit hand-wavy here with how we go about doing this analysis. We don't have any rigorous tools to use this next. The rest of the lectures this week, Wednesday and Friday, are all about kind of coming up with formal tools for doing this big O analysis. So we're going to be a little bit hand-wavy, but just bear with us because I think the idea is still important. So the pop operation, removing something, is just going to be a constant time operation, an O of 1 operation. Because all you need to do is just change top to point to top.next. And maybe return whatever the value was that was previously at top. And you might be thinking, oh, wait, isn't that like 3 or 4 steps? I don't have the code in front of me. I'm not going to actually count it. But remember, this big O notation is trying to give us a rough estimate. It's trying to say, what complexity class is this thing in? And so we don't care about 3 steps versus 4 steps. We're worried about how this scales with the size of the data structure. So if I have 100,000 things in my stack, how many steps does it take, approximately, does it take pop to do? Well, pop just has to change like 2 pointers. 1 pointer, really. That number of steps business does not grow proportionally with the size of the stack. And so we say it's constant there. We drop those lower order terms to hide away some details because it's an approximation. Similarly, peak will also be constant. We just look at what's at the top and return that number. Size and isEmpty are also constant because they're just returning some. You don't have to loop through the list or the link nodes or anything to compute that if we're storing a size field. So remember, importantly, I'm saying we are going to store a size field here, so it makes it easier for us to keep track of these values. We don't have to do any looping for them. And so now what I want you to do is I want you to think about what is this worst possible runtime of the push operation. So take a second. What is the worst possible runtime of the push operation using this linked node approach? Okay, so there's usually 2 common answers for this. Usually people think it tends to be constant or linear time. It turns out here it's going to be constant. Just like our pop, pushing only has to rearrange a couple of the pointers. You just change top to point to the new thing, and you make that new thing point to what was the top used to look at, just like in our animation before. So even if the list has tens and thousands of elements in it, you only have to rearrange a couple things in order to push an element at the top. And so that's going to be constant work. You don't have to loop over the whole list of numbers in order to get that to work. And again, remember, we're being a little bit hand-wavy here, and that's okay. We'll have some more concrete tools to analyze these later this week. But right now, we're trying to get intuition, right? When you're only doing something at like the beginning of the list, you're only modifying a couple things, it's going to be constant. If you're going to have to loop over the whole list of numbers, then we're going to start getting into that linear territory. Okay. So now I want us to pivot a little bit. We just talked about implementing a stack with a linked list. You might be wondering, are there other ways of implementing the stack ADT? And there definitely are. There are lots of them, but let's talk about one other. So instead of using linked lists, let's think about using an array. Maybe create something like an array stack. And in this array stack, we will store an array kind of like an array list. The array will be bigger, it'll be roomier than we need. And we'll also keep track of the size. And now we kind of have to decide, how am I going to use this concrete array to represent this abstract idea of a stack? And so you could imagine I'm going to put the numbers inside the array. I'm going to put the values in the stack inside the array. But one question you might ask is, what order might you want to put them in? Should the top of the stack be index 0 and I add everything afterwards? Or should I make the bottom of the stack index 0 and add to the right? And one way to figure that out is to think about it, like think through what would happen if I did it this way versus what would happen if I did it this way. Think of the pros and the cons. We're thinking about design decisions here. I'm going to just tell you, it makes more sense for our implementation to keep the bottom of the stack at index 0 and add things at larger and larger indices. So if you're going to push the number 3 on an empty stack, you put 3 at index 0. Now when you push the number 4, 4 should become the top of the stack, so we're going to put it at index 1. And so all of this pseudocode over here describing these behaviors are saying use the end of the range of numbers. Put the new number at behind all the other numbers in this array so that the top of the stack is at the end of this region of numbers. So when you pop, you're just going to return whatever is the last thing you added and take that off, take the size down by 1. And we could have that same discussion we did on Friday with, do you actually need to delete that number? Or you just decrease size? Either option is fine. The only other thing I have to add to describe what's going to happen in this array implementation is push gets a little bit more complex, just like with array list, if we run out of room. So if we fill up the available array, then we need to do a resize operation, make a new array that's much bigger, so it becomes roomier, and then copy everything over. Okay? And then I showed if you push 5, you put it back on the top. So let's try to use our analysis tools. And again, a little bit hand-wavy, but let's try to think about what are the runtimes for these various operations. So let's think about pop. Well, if I have this array here, and the top is the size at index size minus 1, popping something is just decreasing size and returning that old value. So even if I have tens and thousands of elements in my array, to do a pop, it only requires doing constant work. I index into the array at size minus 1, and one of the things is indexing into an array is a fast operation. It's just one step in our step counting process. And then you decrease size by 1, yet another constant step. Constant work plus constant work is constant. So pop, simple operation, does not require looping over the whole data. Peek, similar. You just return whatever is at that index, the size minus 1 index. Size in is empty, just like with our linked implementation, we have the size field, so we just know those answers. We don't have to do any computation that loops over the whole array of numbers. And just like last time, I want you to pause and think about what will happen with push. What do you think the worst possible runtime of push could be? Okay, so now that you had some time to think about that, this one's a little bit trickier. This one's much more common to have a decisive split between constant work and linear work. And in some sense, both of those answers are right. It's both constant work and linear work. It depends on when you're pushing. If you pushed when the stack was full, sorry, when the internal array was full, then we're going to have to do this resize operation, which means creating a new array and copying all of the data into that new array. Well, if I have n things in my stack, that copy operation is going to take O of n time. It's going to take linear time. So if we have to do a resize, it's going to be O of n. However, in the case where we have extra room, extra capacity in our array, then it's just going to be a simple O of 1 operation. We add the number at index size, increase size by 1. Easy peasy. We don't have to loop over all the numbers there. And so in this context, the runtime depends on context. And so you might be wondering, well, which one of these is the right answer? Is O of n the right answer? Is O of 1 the right answer? And with what we've seen so far, we don't have the tools to quite easily handle this situation and say, here's the one definitive answer. Because there are really two valid answers. It's linear if you have to resize, and it's O of 1 if it's constant. And that fact that there's two completely different behaviors has huge implications on the decisions you make. Because this O of 1 growth rate is just constant time, while this O of n growth rate is increasing. As you get n bigger and bigger, it's going to take longer and longer. But which one of those cases you run into depends on what the state of the stack was at any point. And so two key insights to keep in mind as a bit of a preview for the tools we're going to talk about later this week is that the behavior in these two cases is completely different. It's almost better to try to analyze them separately than to try to come up with just one number that describes both. And you might think of disagreeing with that sentiment at first, and that seems totally reasonable, because you said, well, I asked in that last question, what is the worst case possibility? And you're right, the worst case is we have to resize. However, with some further analysis that we're not going to be able to do in this course, you can actually show that that resizing operation doesn't happen very often. It's actually the case that this constant time behavior happens way more frequently than this resize behavior. And so most of your times it's going to be constant time, and it's only very rare it will be linear. And so in some sense, O of 1 is actually a much better description because that's what's going to be happening most of the time. And so this tension of which one is right kind of hints at the fact that maybe trying to come up with one number for this actually might not be the right idea. But we might need some more complex tools to go about thinking about how to analyze these cases separately. And the other insight to keep in mind is big O is a tool. It's a tool to describe a runtime. Another term to use instead of tool is a model. We're trying to model what's happening in this code. And George Box, who is a famous statistician, he's attributed to this quote of, all models are wrong, but some models are useful, which is exactly true for big O. Anytime we're doing these simplifications, it's straight up wrong because it's not capturing all the complexities of the real world. But that does not necessarily mean that this tool is not useful. And big O is just one possible tool. There are many possible tools to describe runtimes. And so having to decide to choose just one or the other would make it a less useful tool because it wouldn't be a complete description. And so the extension of this tool that we'll talk about this week lets us consider these cases separately.